The rest of Chapter 5 will all be about different ways that we can determine the enthalpy of reaction. There are going to be 5 different ways to find the enthalpy of reaction. Just a heads up, we're going to study calorimetry in section 5.5. We're going to study Hess's law in section 5.6. We're going to study enthalpy of formation, or delta HF, in 5.7. And then lastly, we're going to do bond enthalpies in 5.8. Enthalpy in 5.8. So this is the rest of the chapter with those 4. So starting with 5.5, calorimetry is a way that we can determine the change in enthalpy of a reaction. Since we can't know the exact enthalpy of the reactants and products, we find that change through heat flow. So what we use is something called a calorimeter. And maybe you've already been like, oh, calorimetry, oh, calories. That is something that is related. And if you've taken a food science class, then you maybe have done this because calories are a form of energy. So to do this, basically the setup is we have 2 styrofoam cups that are tucked together, and the styrofoam cups are tucked together in order to provide insulation. And we know that insulation makes it so heat cannot escape. And then you have your reaction happening in there. It could be a reaction with water, a reaction where you mix 2 different things together, 2 different aqueous things together, substances. You also put a lid on it to help, again, prevent heat from escaping. You have a stirrer to help mix the solution and a thermometer. So, one thing you want to keep in mind is a topic called heat capacity. This is an intensive property of a certain substance. And the definition is the amount of energy it takes to raise the temperature of that substance by either 1 Kelvin or 1 degree Celsius. The specific heat is a little different because it's specific to the mass that you use, and that is the amount of energy it takes to heat 1 gram of the substance by 1 degree Celsius. So it really tells you how easy or challenging is it to change the temperature of your substance. If you've ever tried to boil water, you know it takes a long time. It takes a lot of energy to heat up water. But something like aluminum or some other types of metals, maybe you put a pan in the stove, immediately it becomes very hot, and that's because metals have a very low, very low heat capacity. And so when you have a low heat capacity, and the symbol is C, when you have a low specific heat, that means it's easy to change the temperature. When you have a high specific heat, or high C, that means it requires more energy, so it's harder to change the temperature. So water is an amazing liquid and substance in general because it has a very high specific heat, especially in the liquid form. It takes a lot of energy to change the temperature of the solution. So we also want to keep in mind the surroundings versus the system here. So when we have our calorimeter set up, our thermometer is measuring the temperature of the solution. So we know if I had an exothermic reaction, then my reaction, or my system, released energy. So it released some heat, meaning that it would have a negative value for the heat. When I have an endothermic process, then our reaction gained heat, meaning we have a positive value for the heat. So that's what's happening with the reaction. But when we measure it with the thermometer is measuring the solution. So let's think about the exothermic situation. With exothermic, heat got released. So if I was to measure it with a thermometer, me, the surroundings, then I would see that the temperature of my surroundings would increase. So that's the temperature of my thermometer. So here, if I have an exothermic process happening in my cup, let's just pretend that dot is my reaction that's happening, then I'm emitting heat. Temperature is going up. But when I'm thinking about the reaction value, the temperature of my reaction actually dropped because there was a transfer of heat. So the equation involving heat is that the heat involved of my solution, which I'm going to also put is the surroundings, what we measure in the lab, is equal to the specific heat times the mass of the solution times the change in temperature of that solution. But what we're measuring as the surroundings, if I want to find the enthalpy of, or the heat of my reaction, I'm going to need to change the sign, because the heat that my reaction lost is going to be equal to the heat that my solution gained. So they're the same value, but a different sign. And then I also want to make a quick little aside, because we know that enthalpy is related to heat. Enthalpy values, delta H values, are measured in kilojoules per mole of reactant. So what we're going to need to do is take our enthalpy of our reaction, divide it by the moles of our reactant, or whatever it tells you in the problem. So keep that in mind when we move forward. So let's do a practice problem. How much heat is needed to warm 250 grams of water, which is about 1 cup, from 22 degrees Celsius, which is room temperature, to 98 degrees Celsius, which is near its boiling point in Salt Lake? So we're going to calculate the heat involved in our solution here is going to be equal to C times the mass of the solution times the change in temperature. So we're going to plug it in. The specific heat of water, which is what we are heating here, is 4.18 joules per gram times Kelvin. And I'm also just going to get used to saying degrees Celsius, because our delta T could be degrees Celsius or Kelvin. I'll show you right now. Our mass of our water is 250 grams. And then our delta T, we started at, so it's final minus initial. Our final that we're ending at is 98 degrees Celsius minus 22 degrees Celsius, what we started at. So then we're going to multiply that all together, and you end up getting 7.9 times 10 to the 4 joules. Now, one thing I want you to think about is this delta T. So we went from 22 to 98. So that delta T is 76 degrees Celsius. Let's find the delta T in Kelvin. So what we're going to do down here is take my 98, I'm going to add 273, and then I'm going to do my 22 and add 273. So what you get is 371 Kelvin and 295 Kelvin. So we always want to change our temperatures first before we do the math. Then if I found the delta T between that, I'm just going to subtract the 2. And when you subtract those two numbers, you also get 76 Kelvin. So as long as it is a change in temperature, you can switch those units between Celsius and Kelvin. If it's a absolute value, so a single digit, you just want to do your adding 273. So let's do a calculation of an actual chemical reaction. So we have a student, and they're going to mix 50 milliliters of a 0.1 or a 1 molar hydrochloric acid solution and 50 milliliters of a 1 molar sodium hydroxide solution. And here's the chemical reaction there. The temperature increases from 21 to 27.5. calculate the enthalpy change for the reaction in kilojoules per mole of HCl. So that's what we want down here. We want the delta H of reaction in kilojoules per mole of HCl, which means we're going to need to get moles of HCl. Assume the calorimeter only loses a little bit of heat and the total volume of the solution is 100 milliliters. Its density is 1 gram per milliliter and its specific heat is basically water. So we're making a lot of assumptions here, but that makes sense. 100 milliliters is our total solution. One thing we want to do is make sure when we do our Q equals Cm delta T, we want to make sure we're using the total mass in our solution when the reaction is happening. So we know that we have 100 milliliters here, but we need the mass. So we get to use the density up here to convert into grams. So we know that we have the density of 1 gram per milliliter. So we have 100 grams of solution. It told us that we had a specific heat of 4.18 joules per gram degrees Celsius. I'm just going to straight go there so I don't have to do additional math. And my temperature got all the way up to 27.5 degrees Celsius, and it started at 21.0 degrees Celsius. So let's find the heat of our solution. Don't forget that this is our solution. So that's our first step here, is calculating that. So what we end up getting, that our heat of our solution is 2717 joules. All right, so we're almost there actually. We want the heat of the reaction, so we need to find the heat of the reaction. We just found the heat of the solution. If you remember from the other slide, so this is step 2, is you're just going to change the sign. So we're going to say equals negative 2717 joules. So that's one step. So heat of the reaction is 1. We also need to go into kilojoules. So I'm just going to do that right here. Step 3, I'm going straight over to kilojoules. So 1,000 joules per kilojoule. So we have that our heat of our reaction is negative 2.717 kilojoules. And then our last thing is to get it per mole of hydrochloric acid. It told us what mole to use. So what we're going to do here is use our volume and our molarity of hydrochloric acid to figure out the moles. So I'm going to do this over on the side here. So we have 50 milliliters of HCl. We need to get it into liters, so we could use molarity. 1,000 milliliters is 1 liter. And then remember that 1 molar is 1 mole per liter, so it's a conversion factor. So we can now go 1 mole per liter. So we do those calculations and we end up getting that our amount of moles of hydrochloric acid that we added was 0.05 moles HCl. So now we're going to bring that down here. So for step 4, we're going to use the fact that enthalpy of reaction is equal to heat of the reaction divided by moles, in this case, moles of HCl. So we'll do negative 2.717 divided by the amount of moles, of kilojoules divided by 0.050 moles of HCl. So all of our units are correct. We are doing the reaction, we're in kilojoules, and we're in moles of HCl. So we plug in all of that math, and then our enthalpy of reaction is equal to negative 54 kilojoules per mole. We're going to practice again because there are many steps. So just to review, our first step is plugging into Q equals Cm delta T. Our second step is then changing the sign, going from the heat of the solution to the heat of the reaction. Our third step is then going from joules into kilojoules. And then our fourth step is converting to moles, or finding the moles of our reactant, and then divide and then plugging into this equation here. So a few different steps. I want you to get comfortable with doing them. I feel like step 1, 2, and 3 are pretty straightforward. 4 is not too bad either, but we just gotta remember that the sequence. So let's practice again. We have 100 milliliters of a 0.1 molar of silver nitrate and 50 milliliters of 0.1 molar of hydrochloric acid are mixed in a constant pressure calorimeter. The temperature of the mixture increases from 22.3 to 23.11 degrees Celsius. The temperature increase is caused by the following reaction. So we have our reaction here, 1 to 1 all the way across. Calculate the enthalpy of reaction in kilojoules per mole of silver nitrate. If the combined solution has a mass of 150 grams and the specific heat of 4.18 joules per gram degrees Celsius. So it could be very easy to just plug in to find the moles of silver nitrate by just plugging that in. But there's going to be another extra step we're going to have to do, and it's tied to something you've already learned. But let's get started on our steps that we know. Let's start with step 1. Step 1, we know that we have to do Q of the solution is equal to Cm delta T. So it told us a bunch of this already. We know, that the heat of the specific heat is 4.18 joules per gram degrees Celsius. My mass, it told me, is 150 grams, because, 50 milliliters plus 100 milliliters with the density. And then delta T, we're going to go, it ended at 23.11 and it started at 22.30 degrees Celsius. So plugging that all in, we end up getting a value of 508 joules. So our Q of our solution is 508 joules. Now, if you remember, number 2, we are going to say that Q of the solution is equal to negative Q of the reaction. So if I want the heat of the reaction, which I do, then I'm just going to change the sign, negative 508 joules. So my solution got warmer, it heated up, meaning my reaction lost that energy. Third step, converting that value. So heat of my reaction, I need to get it into kilojoules. I'm going to do negative 508 joules, go straight into kilojoules, 1,000 joules per kilojoule. So we get negative 0.508 kilojoules. All right, the last step, which usually can be pretty straightforward, but in this case it's a little trickier, which I made it that way actually intentionally. So as a review topic, so we're mixing 100 milliliters of silver nitrate and 50 milliliters of HCl. So even though we have more volume of silver nitrate, we need to figure out when does the reaction actually stop. Because if I have extra silver nitrate that didn't get used up, it's not going to be part of the reaction. So what we need to do is figure out the limiting reactant. So I'm going to go over to the side here to do that. We had 100 milliliters of a 0.1 silver nitrate solution, and we had 50 milliliters of a 0.1, this would be molar, hydrochloric acid solution. So let's find out how many moles there are of each and convert to a product to see who the limiting reactant is. So I'm going to start with this one. We start with our volume, 100 milliliters, and I'm going to go 1,000 milliliters per liter, and then I could use my concentration to do 0.1 moles per liter, and I am in silver nitrate. So now I'm going to convert between moles of silver nitrate to moles of, let's do silver chloride. It doesn't really matter, but we're just going to pick a product. Now the ratio is 1 to 1, so we can find out that the amount of moles we have of silver nitrate is 0.01 moles. of silver chloride from that silver nitrate. Let's do the same thing with the hydrochloric acid, 50 milliliters of it. We're going to go to milliliters to liters. Same concentration. It won't always be, so this is why it's good to practice. 0.1 molar. And then we also have, we go to our reaction, 1 mole of HCl for 1 mole of the silver chloride. Okay, so plug that on in and we get 0.005 moles of silver chloride. So if you remember, this means that our hydrochloric acid is our limiting reactant, so not all of this 100 milliliters is going to react, so we need to find out how much will. So let's start with our limiting reactant, 50 milliliters of HCl. And we're going to go to moles, so 0.1 molar. And then we get to go from moles of HCl. 1 mole of HCl is 1 mole of silver nitrate, meaning that 0.005 moles of silver nitrate are actually reacting. So that is very good to know. That actually solves it for us. So we can move that over to step 4, which is figuring out the enthalpy of our reaction, which is equal to the heat of the reaction divided by the moles, in this case of silver nitrate. So we'll do our negative 0.508 kilojoules here divided by 0.005 moles of silver nitrate. So let's plug that in. And we end up getting a delta H value of negative 101.6 kilojoules per mole of silver nitrate. So this was just a review over here about limiting reactants, but keeping in mind we do want to find out who's limiting, who's excess, and if we have excess, we don't want to use all of those moles because they all didn't get used. We only want to use the amount that actually reacted.